Swayam Prabha. Digital India. Educated India.
Okay, in the last class we were looking at the lateral force development. Due to other reasons than just taking a turn and maneuvering. In other words, we found that even when the vehicle runs straight, there are lateral forces, and these forces are generated due to three factors. We saw one is that what we called as ply steer. Okay, this is because of the fact that there are what we called as belts or composite material, and we found that these composite structure, which are due to the steel, for example, in the case of truck tires, which are called as steel, all steel radials, right? Or steel radials, if it is called, then the steel is the material which is used as a reinforcement for the belt. It runs at an angle, and we said that in the composite laminate ply theory, when you stretch this kind of composite material, there's a coupling that happens, and that when I stretch it, there is going to be a moment, or in other words, force and moment, there is a coupling term that's there. One of the questions that was asked by her is that she said, what is this constitutive equation? You suddenly said m versus kappa, right? What is this m versus kappa? Okay. Yeah, I know you might not have had the background in composite material, okay, and you might be wondering why this suddenly one kappa is coming, and why is that it is just not sigma versus epsilon curves and so on. It's easier to write that way. You can solve any of these things, any of these structures using a general three-dimensional concept, but that's not the way it is done, because for bending we have, for example, beam. So if you look at beam, how do I look at this kappa? If I look at beam, all of you know m by I is equal to E by R. Of course, it's equal to sigma by y, very famously written, right? So I can, for example, rewrite this equation as m by, I'll just remove that, EI by R. So what exactly have we done? Note that I have, say, for example, a beam, say a simply supported beam, and say that I have some uniformly distributed load on it. Okay. So what essentially have we done here? So there is a displacement, there's a displacement, of course, and which results in a radius, in other words, change in curvature. So 1 by R is the curvature, and so I can write that as EI into kappa. Okay. So you see that even in your regular strength of materials, you had used, or you had learnt that there is a radius change. Of course, many of you wouldn't have used this equation. The equation that is usually used is m by I is equal to sigma by y is what you would have used. You might not have used E by R. I just wanted to point out that it is not a very new equation or new way of writing. It's exactly what you had written in your earlier classes. Clear? Okay. The other one, if you remember, so in other words, what did we do here? We changed the curvature. This is exactly what we said. We are changing the curvature. Imagine that I had a beam like this, and I'm applying a load, and changing the curvature like that is essentially what you did when the tire rolls. You change the curvature as it hits the ground. Clear? The other one which we saw is called as conicity. Okay? We said that conicity is basically because of the unsymmetric geometry that results when a tire is inflated, for example, due to, say, a belt shift. Okay? And that produces a force, and depending upon which side this belt actually shifts, the conicity also would vary, whether what they call as the serial side, where things are written, or the other side. Depending upon that, there would be a change. Okay. Now, there is, as I said, there's always a confusion whether the tire is moved in the clockwise direction, anti-clockwise direction, the forces change or they keep the same. There's a lot of confusion on that. The ply steer, please note that the ply steer, for example, if I have let's say that that's the top belt by which it is represented. And if I have a force that's acting here, imagine that even if you rotate it, it would look like this. Right? This point, say for example, may go and take that point, so it would look like this. So actually, you do not rotate a tire in the clockwise and the anti-clockwise direction. So it's always clockwise direction. It always looks like this. So the ply steer forces will be acting like that. Right. The last one which we talked about is due to, remember we talked about the ply steer residual aligning torque, and this is also due to the tread patterns. Okay? We said that tread patterns are again, so let's say that I have tread pattern like that. And just simple way of representing, but tread pattern is much more complex than that. And we said the tread also has a coupling term. Right? We saw that the day, and that results also in a lateral force giving rise to a longitudinal force and vice versa, and because of which there is a torque that is created, and this is what we called as ply steer PRAT. Okay. There are standards for this, how much it should be. Some of them may say that PRAT should be, Pratt should be 0, and so on. And so what we call as the design of tread has a lot to do with many things. One of them being this. The other, of course, the most important thing is how water is carried and so on. We'll have a brief discussion on that in one of the later classes before we close this tires. Okay. So this has a number of effects. This kind of the conicity and ply steer has a number of effects.
So for anything to happen, there is need of an external force.
Yes.
It is from the road, right? Road tire interaction.
Yes.
So how are these linear properties converted to road tire interaction?
Yes. So the question is that all of them happen due to road tire interaction. So what happens because of these properties or because of these forces generated? That's the question, right?
How do these properties convert to
Forces, yeah. This is exactly what it is. So when you say, for example, if I have a tire, so what really, in other words, I'll just pose this question slightly differently. So what happens to these forces? What are the result of this? Do these forces really happen when the road tire interaction is there? And because of which, what would happen to the vehicle? Right? This is the question. Good question. Very good question. And let's see what happens to the vehicle. So in other words, first thing is that when I roll the tire on the road, remember that ply steer is due to the change in that curvature. So when I roll the tire on the vehicle, okay, automatically a force is generated. Okay, a lateral force is generated. Right? So lateral force is generated in the front and the rear. Let's say that that's my rear tire. Let's say that is the vehicle. Okay? Now, I have a number of forces that are acting. Let me do that. Let's say that that is the, say, a force due to pleisthere. Let's give some values, okay? Taken from an original paper, say, let's say that I have some values. Then I have other forces, right? Conicity force. Let's, for example, for the time being, this talk, we will just leave it for the time being. And we will look at conicity forces. Okay? Conicity forces depend upon, as I said, because of this belt offset can be in any direction. Okay, let's say that it hangs in this direction. All right? And it can be anything. It is not a constant because it is due to the manufacturing and so on. Let's say that it is 25, 20, or 15, 10, or whatever it is. Okay? Then the rear tire, let's assume that they are the same as 70 because the tire design may not be the same, but let's just assume that it's 70 or 60 or whatever it is. Okay. Let's say that the rear conicity factors is, say, 10 in this direction and 20 in this direction. Right? Now, so in other words, definitely there is an imbalance in this vehicle. Okay, the force distribution now, remember that it's going straight. Clear? Now this is the distribution as it goes straight. So what's the effect of this kind of distribution? Obviously, the vehicle is not going to go straight. Okay? So there will be a tendency for the vehicle to actually travel like that. Okay? Right? There will be a tendency to pull. In other words, there is a steering pull. So you have to constantly steer the vehicle in order that it goes straight when these force distributions are not uniform. So one of the things that you can do is to actually shift the tires so that this kind of distribution is not bad. You can eliminate it completely, difficult, but at least you can make it small. But what's the effect of this? The effect of this is obviously that I'm going to constantly steer the vehicle, which means that this force, opposite force, have to be generated, which means that there will be a slip angle, and hence there will be wear. Okay, these kind of forces would cause wear, and that's the reason why wear will depend upon whether it's a front or the rear, and that's the reason why there is always a rotation. What the tire companies call as a rotation plan, so that the forces that are generated does not harm the wear of or does not accentuate the wear of the tires. Right? So this is what is the effect. There's the other effect which is called as dog trailing, when the rear gets shifted and the vehicle and the front is like this, and that's what is called as dog trailing that happens.
The direction
Yes.
of the conicity forces, why are they different in the front and the rear?
Yeah, no, I'm just doing that arbitrarily. Okay, you can have 15. That's why I said this can be 15, 10, 15, 5, 0. And
What about the magnitude?
yeah, that's exactly. So the direction, so this is what we plotted, if you remember, that if I go to a factory and if I take 100 tires, okay, and then plot the lateral forces, say for example, that's the lateral force. Forget for a moment pleisthere. I know what is the pleisthere value, okay, so I can find out what is the conicity value. Then the distribution would something be like this. So in other words, there will be positive, this is what is this, number of tires. The lateral force distribution will be something like this, because I said that this is due to belt offset, and belt offset can be in either direction. So because of which you will have a minus lateral force and a plus lateral force. Okay? Whether the cone is going to become like that, or the cone is going to become like this. Why is there a cone? Remember that when there is a belt, okay, and when there's a belt in the tire and the belt gets shifted, one side becomes stiff, the other side is not as stiff as this. So in other words, just go to only the crown of the tire let's say that that is the center, okay, and that's the buttress region and so on. Let's forget about that for a minute. And so I have a distribution of the belt, and if the belt now is offset, is say for example, instead of being symmetric about the center, if the belt happens to be something like this, okay, offset in one direction, we saw those belts the other day, and when the belt is shifted, then due to inflation pressure, okay, so now the belt is like this. So this side, due to inflation pressure, would go up more, okay, than this side, which is stiffer because of that belt offset. So it would not get a nice symmetric shape, and the shape of the tire after inflation would look something like that, in fact. Okay? So the crown of the tire is not going to be symmetric, but would incline. So when this tire is rolled, you produce what is called as the, okay. Now, unfortunately, these are not the only things which produce lateral forces. The lateral forces are also produced by what is called as the camber. This is actually a motorcycle camber exaggerated, just to illustrate a point that there is a camber. And the camber, you know about camber, and the camber also produces a thrust. Yes?
Why do we have the offset in belt?
We do not introduce that. The offset, why is that there are offset in belts? This is a manufacturing process. This is due to the manufacturing process. As the tire is built, the belt is placed, okay, on a drum. So, and then it is taken over to a curing press, okay, and it goes through what is called as a curing process. So when this tire is manufactured, when they're placing the belt and then cured and so on, the belts do not stay in place. Remember that these materials are viscoelastic materials. And the viscoelastic, it is when it is in a stage where it's in a pre-cured stage, when the curing has not yet taken place. Okay, it's in a pre-cured state. Okay, its viscoelastic property, it becomes highly viscoelastic. In other words, it starts flowing in a very short time. So due to so many reasons, these belts are not necessarily symmetric. So this belt gets, is offset.
Then why can't we put longer belts? So we won't have
Whatever be the belt width, it's going to shift. Okay, there are other things, into design. Is a good question, but then we are going into tire design. There are very good questions. Why is that we just have a long belt and be done with it? One of the cardinal principles in tire design is that your belt's edges are singularity points. Okay, and as far as possible, you do not get the singularity point into regions where the stresses are high. Okay, you don't get that singularity point. It is what is called in our mechanical engineering design as stress racers. So the tip of the belt, okay, is a stress racer. So it's good not to get that into a region where the stresses are already high. You know that when you have a very sharp corner, for example, which is a singularity point, then you will have stress concentration. And so when there is a stress concentration, the stresses increase. Okay, so that's the reason why you can't have as long a belt or as big a width of the belt as you would like to have. Okay, because you would now enter into regions where the stresses are high, so the belt edges would become very vulnerable. Right? Won't be able to go further than that because of lack of time. But tire design has so much of engineering principles. It's such an exciting field because there are so many things that act. So in fact, if you look at tire design, you would learn the mechanics of material at the highest level. Okay? Because you are dealing with a composite material. You are dealing with a material which is not linear. You are dealing with a system where not only failures you have to avoid, which is very, very important, okay, but also the durability, the wear characteristics have to be very nice, very good. You have to design it such a fashion that handling characteristics are not affected, the noise of the tire is low, the doesn't produce vibration. Oh, you have covered the whole of engineering. Right? So that is why tire design becomes very exciting, because the whole of engineering, whatever you have learned, tell me a course and you have an application here. You studied, for example, long chain macromolecules, right? The behavior of macromolecules in your first year. That was your chemistry course. So macromolecular chains, how they act, completely forms the basis for the behavior of the tires. Okay, how does the macromolecule, this is a macromolecular structure. This is an elastomer. So whatever you studied in chemistry is applicable here. So tell me a course and I'll tell you where it is applied in tire. So that's why it's very exciting, right? Okay, come back and we will look at this. Does that answer your question? So there are forces. But unfortunately, the forces do not stop there, and we'll come to the camber part of it. Okay? There are two things that are important. One is the camber of the vehicle. Okay? It can be 0 camber in a car. It can be 0.5. It can be 1.5 in a truck, and so on. Okay? So there is a camber of the tire. The camber of the tire is superimposed on the camber of the road. Right? So there are two cambers and they act together. So for example, the camber of the road can be like this, and the vehicle can be going here like that if it happens to be a 2-lane traffic, and in some of the what you would call as kacha roads or village roads where it may not be like this, you may be going in this way, where there will be one and so on. So these kind of cambers are given for the water to be drained out, and so that is also going to have an effect. And what's the effect? The effect of camber is to give what is called as the camber thrust or camber force. From the point of view of vehicle stability, this becomes very important in a motorcycle tire. From the point of view of wear, especially in truck tires, the camber thrust becomes important. Let's see just what happens. As is our practice, let us go and sit down in the tire and see what really happens and how this force is generated. Okay. So assume that there is no road. If there is no road, actually, this would be the tire profile. Okay, that would be the tire profile. Imagine as if it is penetrating the road. Okay, now when you roll it, the tire would take an elliptic curve, goes like that. No, that's not the case. The road has an important effect, and the road actually pushes a point, say for example, which is here, okay, onto this position. So let me call that as P and or P1 and P2. A P1, a point, if you go and sit at a point P1, you will not be following P1, but you will be shifted to P2. Okay? Right? You will come here. Is that clear? So this is actually the shape that is taken by the tire is that, what is seen in the white line. So in other words, there is a shift in the Z direction, if I call it as the Z direction, and there is a shift, okay, in the Y direction. This is our Y direction, right? So this is a shift. Of course, this shift in the Z direction produces from the road that reaction which we called as Fz. Remember that this is what we did all the time before. But the road also pushes this point, okay? So it goes like that and then goes like this. So just exaggerate that. So from here to here, when a point is pushed, which we call as P1, and the other one is P2, okay? So it takes the route from here to here and here to here. So in other words, there's a force which actually pushes the point in the lateral direction so that the P1 reaches P2, right? If you look at the plan view, then for example, the points which are lying here are now completely shifted in the plan view to points here. So I'll get a number of points which are here. So these points now go to those places. Okay. So because of this pushing of these points, I develop a force. Right? So that force is the camber thrust, and it acts like this. So there is again a lateral force that is generated. I didn't do anything. I didn't even corner. Okay? Again, a lateral force is generated due to the camber that is present either in the vehicle or on the road, and the result is that that is to be added to the forces that I already have. So the camber thrust produces a lateral force.
So actually camber is powder like
Yeah, camber, yes, this is a positive camber and a negative camber. You know, we are looking at camber just in one of the, say, for example, there's a camber I've provided, okay, depending upon, you can have a camber like this, or you can have a camber like that. If the camber is in the opposite direction, the force will be in the other direction. So it doesn't make a difference how the camber is. For example, you can look at it as a motorcycle which is taking a turn, where you're just leaning, and that's what happens. Clear? So the thrust, of course, depends upon what the camber you give. Okay? And also, please note that the camber is quite complex, is made quite complex because of the road. Okay? Let's say that I have a camber which is given like this. I'm just exaggerating. Okay? It's very important for trucks, and it's very important that the truck manufacturers actually look at what is their camber. You know, they give a big range, but that would have a lot of effect on tire wear. Okay? And it also goes with the road camber. Now, this is straight road. Okay? Suppose you are going like this in the road, then what would happen to the road? The road is inclined. Road is given a camber. Okay, what do I mean by road camber? That's the question. The road is always not straight. It's not a flat region like that. Right? A road is given a camber, and the road camber is, say, for example, is something like this. Why do I give this? Because when there is, all of them are exaggerated. Will be so, you know, like a mountain. No. We're talking about 1 degree. This angle is in India, usually it's about a degree. Okay? Now, this may vary from place to place and so on, but let's say that it's about 1 degree. Okay? Why are we giving it? Because it is a beautiful drainage that has to be provided. Go and look at any road, you wouldn't have noticed it. Stand here and look at it, you would see that camber given automatically. Right? So it would be not so sharp, okay? Something like that. Right? So now, if this is the flat road, let's say that this is the camber, and now I'm going to change the camber of the road, okay, and make it, say, like this. I'm giving a camber. Right? So what happens now? What was sitting, this is the angle, now it becomes, that's the angle. Okay? And what was this angle, it now becomes that angle. Right? It is something like, it's like this. I change the camber of the road, okay? Or in other words, I put one more angle. Let me draw that clearly. Let's say that that's the road. Right? I have an initial angles. Right? So now I'm giving a camber to the road. So the road camber, I'm putting it like this. Okay. Now the tire is going to now sit like this. So there are two angles now. This is how the tire is now going to sit, right? So in other words, what was straight here, you have for this side, you have rotated it in this direction, which means that you have made it more towards zero camber or reduce the camber. Okay. Now what happens this side? Now this side actually it's actually going like that, sorry. Actually it is going like this. So in other words, this angle now is now reduced.
Or we can just look at the vehicle inclined like this. Gravity is the only thing that.
Yeah, gravity is, yes, of course, gravity is always acting in that direction. Gravity we are not, of course. Yeah.
But that is the only thing that differentiates, say, a 0 degree and a 1 degree road, right? Camber.
No. This is geometry. This is geometry. Please note that I can't resolve it. It's not, camber is not resolved. Note that carefully. Say, for example, let's forget about the road for a minute. Okay. So suppose I have, this is very important with the point which you said. Suppose I have a camber like that. Say, here, let's take this. Okay. So let's say that, let's forget it for a road for a minute, that makes it complex. Let's say that I have a flat road where I have a camber. And how does the load act? What you called as gravity load, say G load, it acts like this. And camber is how? How does it act? Perpendicular to it. So how can you resolve a perpendicular force into a vertical force into a horizontal force? You can't resolve it. So camber is not resolving the force, okay, along a horizontal direction. This is a very important point. Camber is because of deformation of rubber. The camber thrust is because of the deformation of the rubber, okay? And that's what we saw here, moving from P1 to P2, right? So you don't resolve it. The effect of camber thrust is, of course, a force that's acting on the tire, which is now, the tire is equilibrated by an equal force on the at the axle, and there are two forces that are acting on the tire.
No, is it equivalent to the situation where on a flat road with no camber, if you suppose somehow, if you are able to generate a body force in the horizontal direction, is it equivalent?
There is no body force involved in this. What is body force? Body force is a force that acts throughout the volume of the body, which is typically your gravitational force, okay, or magnetic force and so on. So this is not a body force. It is a force that's acting at the tire road interaction. I mean, due to tire road interaction, and is acting at the interface between the road and the tire. Clear? So it is not a body force. Body force means it would be acting throughout the volume of the body. So I know this confusion, I understand this confusion, that many people think that camber is due to an inclination and resolve this in this direction. That won't work, because this force you can't resolve it to get this force, right? Okay. So in other words, if you look at road camber, you just look at it as if there is a change in the camber angle. Okay. So that is what is called as a camber thrust or a camber force, and that is added to all these forces that are happening there. Right. So the situation is not that straightforward. That's why this is so exciting. So the tire manufacturers recommend that you rotate the tire, because so many forces are acting, you do not know the forces, and these forces have an effect on wear, and you want a uniform wear. Best thing to do is to have a rotation plan. Okay. Right. Let's get back into the so one more derivation which I have to do, and we'll stop here for a minute or maybe for 5-10 minutes of this class, because I know that you have a quiz coming up, and if there are questions, you can ask them so that we will clarify, some of them. Okay, now, yes.
Camber also give, conicity is also called camber.
No. No, camber is from the vehicle. Okay, conicity is from the tire. The tire becomes a cone. So the reason is not the same. Okay, the deformations may be similar, but the reason is not the same. When we say camber thrust, okay, it is coming from the vehicle where I give a particular camber. Right? So hereafter, when you look at a tire, go and see what is the camber, how the wear is of the tire. Okay.
Camber, we are referring camber force is to be the deformation in tire in the rubber.
Absolutely, I agree with you. So this is due to deformation of the tire, and so the origin is tire. Ultimately, the force origin is due to an interaction between the road and the tire. Beautiful question, no doubt about it. But why is that interaction taking place in camber? The interaction is taking place because there is a voluntary camber that is given, okay? And that camber is what is causing this kind of minute deformations that are taking place at the interface. Right? On the other hand, the shape of the tire, when it is put in the road, is changed by the road, not by the road, okay? It is first changed by the manufacturing defect or whatever it is, okay? Then there is a deformation in the road which makes it flat like what we have said, and then it causes. So in that sense, both camber thrust as well as conicity is produced because of deformation of the tire which is running on the road, no doubt about it. Any other questions?
Can you just go through PRAT again?
What is PRAT? Unfortunately, we don't have these the slides, but I hope you remember the slides, right? Remember that when the question is, don't understand how do you create PRAT? The direction. And what is PRAT, right? So this is a very simple thing which I did, but let's understand what it is, okay? The fundamental reason for this PRAT is what is called as unsymmetric behavior, okay? Called as, say, unsymmetric bending and so on, right? So it is the unsymmetric bending. You're going to face this quite often in your next course on automotive structures. You're going to look at unsymmetric bending very closely with lots and lots of equations. So the equations can wait for some more time. But let's look at what is unsymmetric bending. All of us had looked at symmetric bending, where there is a symmetric, say for example, it can be a rectangular beam or a square beam where there is a, very clearly draw it. There is a symmetric, this axis is symmetric about, the geometry is symmetric about the two axes, right? Now, when this, say for example, I have a cantilever beam, and when it is symmetric, okay, and you bend it, when there is bending, then it would not get, suppose I displace it, okay, I displace this, and then the displacement would be only in this direction and would not get displaced in the other direction, which I would call that as x. Okay. Now, if my loading is not in the same direction as this, or in other words, if the loading is the same, but if the structure does not have symmetry like this, say for example, I have a structure which is like that, okay, and then I have my axis is defined like this, and I have a force that's acting, okay, in the y direction, and that being the y, then the displacement is also in the x direction, okay? So a y force also produces a displacement in the other direction. When would it not produce? There exists what are called principal axes for this kind of structure, okay, which may run like this, let's call that a psi and eta, which we're going to see in the next course, that if you apply forces along these principal axes, then this kind of coupling would not take place. So there exist these principal axes about which, say, for example, if I apply force along the psi direction or eta direction, there won't be any displacement in the psi direction and so on. But as long as there is an unsymmetry in this kind of loading, then it would produce a force in the other direction. Okay? Clear? So now, this is the fundamental. Now I have lateral forces and longitudinal forces even in free rolling. Okay? Let's say that I'm doing a free rolling of lateral forces and longitudinal. You've already seen that there are forces. Say, let's say that this is my tread profile at a particular region, at a particular point. Okay? So this is that's the, say, contact patch. Okay? I have tread profiles like that. And let me say that I have at the edges tread profiles like this. Okay? Now we have seen, for example, that the lateral or the longitudinal forces. Yeah, any questions? There are longitudinal forces that are acting. Okay, this is the leading edge. In other words, that's how the vehicle moves. There are longitudinal forces at the either end. Okay, and remember that's a positive and then comes back negative. The longitudinal force. Right, and there are also lateral forces in other directions. Okay, which is spreading out. So there are lateral forces at the edges, at the shoulder of this contact patch.
Is this because of the sidewall or is this the...
Yes. There is a sidewall which there's a thrust and because of which there is a lateral force that's happening. Okay, that's what we saw on the last slide. Right? Remember that we said in contact patch there is a local effect, there's a global effect and all those things. Let's forget it for a minute. Okay, let's say that I have in a tread which is something like this. So now these guys are going to now produce additional forces which are perpendicular to these forces which are actually thrust on them because of the contact patch. So there'll be a force like this, there'll be a force like this, there'll be a force like this, and there'll be a force like this. Right? These are due to the coupling term. Right? So these coupled forces now create a torque, okay, around it. Now, question is, are the treads as simple as this? No. We're not saying that the treads are as simple as this. But you can use, for example, finite element analysis in order to understand what is PRAT, how it's produced, and what are actually the shape of these treads, and all those things, blah, blah, blah. You can do that. Okay. So actually, the next question is, can I treat the tread like simple cantilever beam? No, these are stubs, because why are we producing, what are the other things that are happening? Because there are shear stresses become important, there are what are called shear deformations, and so on. All of them are brought out very cleanly by a finite element analysis, and the theory of which, as I said, we will learn later. Okay, is that clear? So this kind of cross-linking due to unsymmetric bending is the reason for what we call as PRAT. Okay.
PRAT is because of the trapezoidal shape.
Yes, this is the shape. That's the shape which is not symmetric. It's not necessary that it should be a shape like this, rhombus or something. As you've seen in any tire, you would see that the shapes are very complex. Okay. The shape of the tread also depends upon its ability or its requirement that it carries water. Right? So that's what it is. Maybe after some time we will see about what is wet traction. We'll go ahead, we'll do lateral, and then we will come back and look at wet traction and so on. Because we're spending a lot of time on tires. I understand it's an important topic, but we have not yet gone to lateral dynamics, which is exciting in its own sense, and how the tire is going to have a huge impact on lateral dynamics is what I'm also interested to project. And we have already entered lateral dynamics in the sense that we now know how lateral forces are developed by the tires. Yeah, any other question? Yes.
So when we have uneven contact pressure, so actually all the points on the ground are actually the axis of rotation, right? Means if we are writing tau equals to I omega, we can write about all the points.
Can you show me what's the question so that I can repeat it to others?
So this thing. So we have done like we have found the F equivalent equals to TR into TR equals
Yeah.
to F into RD.
Yeah.
About this thing.
Yeah.
So actually all the points are equivalent in this case. So we can actually can we apply about the point where the equivalent P is?
Yeah. See, in other words, what the question is that how. So suppose that is the. Let me understand. Let me see what I understand from your question. Suppose that's the contact pressure distribution which we said, okay, which is unsymmetric because of the viscoelastic forces, right? And there is a contact force that's the whole of the reaction that's happening like this, okay, and that is going to rotate the tire in the opposite sense, in the sense that there's a torque. Okay. The question is, can I just replace all these forces that are acting by an equivalent force there? Of course. Of course. Okay. And that causes the moment. Just 1 second. Right. So in other words, oh God, I removed it. Maybe what Apurva drawn. I've drawn it beautifully. I'm going to only replace that. In other words, when there is camber, for example, look at a motorcycle. Okay, there's a lot more to it. We are not. There's what is called a stern slip and so on. We are not entering into a lot more tire mechanics and tire dynamics. But please note that the complete force doesn't act right at the center of the contact patch. It acts here in this case like this. If you look at it from the top, it acts actually to the side, which gives a overturning moment. So in actual case, okay, that gets deformed, and so the force is acting like that. Okay. So in other words, completely resolved forces do not act symmetrically at the center, because of which there are so many moments that are created. Clear? So can I replace the complete contact pressure by means of an equivalent force? That's the question. Of course you will do it. And of course that's what we did for all the longitudinal forces, and that's exactly what we are going to do for the lateral force. So for the lateral force generation, we're going to look at the equivalent force as well as a moment, okay, which we called as the aligning term.
What are the effects of moments on other directions?
Yeah, no, absolutely. There are moments in the other direction, okay, which is an overturning moment. There can be moment which tries to overturn, okay, which is, say for example, you have the three directions, okay. So for example, this is the traveling direction of the vehicle. Say let's say V, and that's the lateral direction of the vehicle Y, okay, and this is the normal to the ground. Yeah, any questions? Just one second.
No, I just forgot it. Why we have unsymmetrical?
Yeah, we talked about viscoelasticity. Remember, that's what it is.
We told like stress loading will be.
Absolutely.
That means
So this is with respect to that, but the other moments are created due to other reasons. Remember that we had what is called as an aligning torque, right? Remember that we had, okay, if it's a plan view, a vehicle which is going straight like that had to take a turn, right? And so we gave a steering angle, and that produced what is called as the alpha, in order that we get the centripetal force, and the centripetal force again does not act right at the center, okay, and acts, if this is the line, that's the center, it acts away, and because of which there is a moment that is generated, and that moment actually makes the vehicle or makes this to go straight again. Okay, so it is called as the aligning moment. So that aligning, in other words, that is the moment, aligning moment, right? And the rolling resistance, because of this, produces a moment about y, right? This is the moment is produced like that. This is a rolling resistance moment. The other third moment in the x direction is because of the fact that there's a camber and the contact point is not exactly along the x direction and can be shifted away from x. So the normal force acts not exactly here but away from it. Okay, look at this. This is the center point, but actually it acts away from it. So because of which, okay, so that is the force that's actually acting, if this is the contact patch. So because of which there is another moment that acts along the x, which is the overturning moment. So there are three forces: the normal force, the longitudinal force which gives the traction or braking, and there is a lateral force which is the centripetal force. Along with it, there are three moments. Okay, these forces produce moment in other directions. That's what we saw now. Clear? So it is not symmetric. The contact patch is not symmetric. That's the most important point. Yes, though you may say we assumed a parabolic, nice parabolic distribution. We're going to do that again in the next class for the combined cornering and braking, but that's an assumption which we made. Okay?
So will that unloading and loading be constant throughout the free rolling? Like suppose the contact patch will be.
Yeah, but then we are looking at the graph which I drew was for a point. See, the question is, how do we view this loading unloading? View the loading unloading from the point of view, go and sit in a tread and look at it. Okay? Actually, the tread is at different positions in the contact patch. So that maybe we'll do that in the next class. And then you see that each one of this point will get loaded and unloaded. And that's the graph which we saw.
But then, sir, how can we assume it to be a constant rate? Like
yeah, because there is a steady state, okay, and every tread undergoes. This is what we call as a steady state, and so every tread undergoes a loading, unloading characteristics. Okay, so you can look at it, view it something like this: freeze the position, and then view it. That's what you get, right? Okay, so we'll stop here and we'll continue the next class on Wednesday.